Now with the third condition, as can be clearly seen here, the condition 1 where this circle is orthogonal to the circle 1 given there in the problem, and the circle is orthogonal to the second equation given out here, and then thirdly the condition is given that center of the required circle lies on the diameter whose equation is given. So here the equation is given to be a straight line in this case. So using this straight line, let's see if we can form an equation where we know that for the circle S equal to 0, center is minus G minus F. That is, this center will be minus G minus F. And using this center, clearly, since center lies on 2x plus 3y equal to 7, that implies minus G minus F lies on this, is how we understand. That means this point lying on this line implies this point satisfies this equation. Therefore, 2 times of minus G plus 3 times of minus F is equal to 7. In place of x, I substitute minus G. In place of y, I substitute minus F, because this is assumed as x and this is assumed as y. So this on simplification gives minus 2G minus 3F equals 7, which on further simplification gives 2G plus 3F equals minus 7, which is equation 7. So I have obtained totally 3 equations, 4, 5 and 6. So therefore the intention is to solve these 3 equations using elimination method to find the 3 unknowns G, F and C. So in order to do that, let's frame all the 3 equations which we have found in the recent sessions. 3 equations in 3 unknowns, solving them through the elimination method. So initially I tried to eliminate C to get an equation in terms of G and F and then solve with this. So from 4 and 5 I try to subtract, so that equation 4, which is 4G plus 6F plus 6 plus C is negative 11, and 10G plus 4F plus C equals negative 21, which on subtraction gives me 4G minus 10G, which is minus 6G, is 21 minus 11, which is 10, is what we get. This on further simplification gives minus 3G plus F is equal to 5 when I take 2 common and divide. Dividing the whole equation by 2, each of the term reduces by half as this. Therefore, I get an equation minus 3G plus F equals 5, which I take it as equation 7. Now I would like to solve equation 6 and equation 7. So taking by equation 6 and equation 7, clearly I see that this can be made equal to this by multiplying 3, so that my coefficients of F are same. Therefore, multiplying equation 7 by 3, I get this equation 6, which is 2G plus 3F, which is minus 7, and this multiplied with 3 gives me 3 times of minus 3G, which is minus 9G plus 3F is 3 times of 5, which is 15. So this on subtraction gives me 2G plus 9G, which is 11G, and minus 15 minus 7, which is minus 22. That implies G is minus 22 by 11 which is minus 2. Therefore, G equals minus 2, which I am going to substitute in one of the equation which gives me F. So substituting in 6 gives me 2 times of G plus 3 times of F is negative 7. And this, on further simplification, gives minus 4 plus 3F is minus 7. That implies 3F is 4 minus 7, which is minus 3. That implies F is minus 1. So G is minus 2 and F is minus 1, which when substituted in either 4 or 5 gives us the value of C. Now that I have found the values of G and F, to find C I substitute in one of the equation. So here I have the equation 4G plus 6F plus C equals minus 11, where I substitute G equals minus 2 and F equals minus 1. So 4 times of G, which is minus 2, plus 6 times of F, which is minus 1, is equal to minus 11. And this on simplification gives minus 8 minus 6 plus C is minus 11. Minus 14 plus C is minus 11, which on simplification gives, which is 3. So therefore there are 3 values which I have obtained. Therefore G is minus 2, F is minus 1, C is 3. So these 3 values which we have found construct the general equation of circle required out here. So let's see how we can find the required equation of circle using the 3 values. So with the 3 equations, I substitute in S equal to 0 such that I get x square plus y square plus 2gx plus 2fy plus c equals 0. With the general equation, I have 2gx plus 2fy plus c equal to 0. That implies this is x square plus y square minus 4x minus 2y plus 3 equal to 0, which is the required equation of circle. So this is the required equation of circle, which cuts the other 2 circles orthogonally and which has its center lying on the diameter of the another line given in the problem. So like this, different system of circles have different conditions through which we find the answers with a similar procedure. So there are many concepts through which system of circles are connected with different procedures. Ultimately, it is the method and the concept which is to be understood more better. Radical axis is a new concept of system of circles, very much connected with the system. So what is radical axis? As we come with the introduction of radical axis, let's recap with the power of a point. Suppose if I have a circle and I have a point P, x1, y1, we have discussed in the previous session that power of a point is the distance from here to the tangent of the circle. So PA is the power of this point with respect to the circle. So using the concept of power of a point with respect to the circle, let's take 2 circles. If suppose I have 2 circles, circle 1 with center C1 and the circle with center C2. So for these 2 circles, let me say if I have a point where the power of the point with respect to this circle and the power of the point with with respect to this circle is the same. Similarly, let me take one more point where the power of this point is as equal as the power of this point with P2. So if I have the set of all points in such a way, the power of the point with respect to either of the circles are equal, then we say the locus of all the points which we join is called the radical axis. So radical axis is a straight line which is obtained from locus of all the points which are equidistant from the two circles. That is, when these two circles have the equal powers of either of two circles. As can be seen here, this point is equidistant with the powers, with equal powers, and hence we get a line which is called radical axis. Now let's see the radical axis for the three types of cases which we have in intersecting circles, in case of the circles. The first case is if I have the two circles which are far apart, then in this case the radical axis is a line which is equidistant from the two circles. So this line is equidistant from the two circles. If suppose I have two touching circles, then the radical axis is nothing but a common tangent. Is nothing but a common tangent. So radical axis of two touching circles is a common tangent. And radical axis of two intersecting circles is along the common chord. That is a secant, a common secant, or a common chord. So in this case the radical axis is along the common chord. In this case the radical axis is the common tangent. In this case the radical axis is a line exactly in between the two circles. That's how we understand the radical axis for the three types of cases: disjoint, touching, and intersecting. If suppose I have two circles, x square plus y square plus 2gx plus 2fy plus c equal to 0, and s dash equal to 0, and the condition is that these two circles are non-concentric because radical axis does not exist for concentric circles. We're non-concentric, then for these two circles the radical axis is given by L, that is s minus s dash equal to 0. That implies s minus s dash, which is given by is how we get the radical axis equation, which is a straight line. So radical axis is a straight line given by the equation L equals s minus s dash equal to 0, the subtraction of the two circles. Radical axis and its limitations. Radical axis does not exist for concentric circles. So this is where we need to understand the reason why the radical axis does not exist for the case of concentric circles. Why is the question. So here, if we take two concentric circles, then we clearly understand that these two are the circles with same center. Two circles are said to be concentric if they have same center. Now, for two concentric circles with one circle lying in the other and having same center, the question of the power of a point, say I want to take a point Px1, y1, and the power of a point with respect to this circle and the power of the same point with respect to this circle is highly impossible to be equal. That is, if I take PA and this is PB, any point we take in this plane, it is impossible that power of this point with respect to this circle, which is PA, will never be equal to the power of this point with respect to the second circle. And therefore, since there exists no point in plane such that power of the point with respect to the two circles, powers of the point with respect to the two circles are equal. Therefore, because of this reason, radical axis or locus of such points does not exist, is how we find the reason. Radical axis or locus of such points does not exist. Therefore, the limitation is for concentric circles, radical axis does not exist. Now let's identify the geometrical properties of radical axis. Radical axis is said to be always perpendicular to the line joining the centers. That is, say for example, I take two circles C1 and C2, circle with center C1 and circle with center C2. You suppose I join C1 with C2, then radical axis is always said to be perpendicular to the line joining the centers of the circles. Is how we identify the property. So L is perpendicular to C1, C2. The line L is always perpendicular to the line joining the centers. We cannot get a radical axis which is not perpendicular to the line joining the centers. Let that be disjoint circles or touching circles or intersecting circles. Now let me take three circles which are having the centers which are non-collinear. So for example, I take circle 1 with center C1 and circle 2 with center C2 and circle 3 with center C3, such that all three are not collinear. The condition here is that the centers C1, C2, C3 are not on straight line. They do not lie on straight line. So when the three circles with centers C1, C2, C3 are non-collinear, the radical axis defines its one of the most important geometrical property, where if I draw the radical axis of this, joining this and joining this, then the radical axis of C1 and C2 is exactly perpendicular and in the middle, which comes out to be this. This is the radical axis L1 of C1 and C2. Next, the radical axis of C2 and C3 is exactly this, which gives for L2 equal to 0. Then thirdly, the radical axis of C1 and C3 is also equidistant and here. And this is L3 equal to 0. The geometrical property here is that the radical axis of one pair C1 and C2 and the radical axis of C2 and C3, which is L2 equal to 0, and the radical axis of C1 and C3, which is L3 equal to 0, all pass through one point, which is a very important geometrical property, which states that radical axis, if L1 is the radical axis of C1 and C2, L2 is the radical axis of C2 and C3, and L3 is the radical axis of C1 and C3, then all three are said to be congruent. Note, L1, L2, L3 pass through only one point of intersection, which we mathematically call as concurrent. So they are said to be concurrent in case of radical axis. The radical axis of each of the circles are said to pass through one point, which is the radical axis geometrical property. Radical center is the point of concurrence of all the three radical axes. In this case, this is called the radical center. Which is the point of concurrence of all three radical axes. Is how we understand the radical center. So the point of intersection of all the three radical axes is referred as the radical center for each of the circles C1, C2 and C3. Now let's see the property of orthogonality of circles connected with radical axes. This is one of the most important geometrical property identified in the branch of connecting the radical axis of two circles. Say for example, I have two circles S dash equals 0 and there's another circle S double dash equals 0, and then I want to find the equation of the circle which cuts these two orthogonally. So geometrically we identify that if there's a circle which cuts this and this orthogonally, then equation of this circle which cuts this orthogonally, S dash and S double dash, is said to be identified. Say I have this circle with equation S equal to 0, then the geometrical property identified out here is that the center of this circle lies on the radical axis. If there is a radical axis for the two circles, which is this is the radical axis for S dash and S double dash, then using this radical axis we identify that the circle which is orthogonal to these two circles has its center on the radical axis. So this is the property. Center of the circle S equal to 0, C, lies on the radical axis of S dash and S double dash equal to 0 is the property which is identified out here. The center of the circle is nothing but a point on the radical axis of the other two circles, where my S is x squared plus y squared plus 2gx plus 2fy plus c equals 0 and my S dash is x squared plus y squared plus 2g dash x 2f dash y plus c dash equal to 0 and my S double dash is x squared plus y squared 2g double dash x plus 2f double dash y plus c double dash equals 0 is how we identify the geometrical property connecting the radical axis with the center of the circle which is orthogonal to this and this. Now let's see how radical axis acts as a bisector, that is as the midpoint. So radical axis sometimes acts as the bisector in the case where, say for example, I take two circles and then I have this with center C1 and this with center C2, then clearly I have the radical axis exactly in the middle. Now this being the radical axis, now clearly the property says that if I draw a common tangent this is the common tangent, then the property says that the radical axis bisects the common tangent. That is, if this is the common tangent where I have P is this, and let me say it makes point of contact A with circle C1 and point of contact B with circle C2, then this will be equal to this. That is, the radical axis as bisector states that. So therefore, here my PA is equal to PB in case of the radical axis. So the property says that if I have two circles where the radical axis is drawn, then if one of the common tangent is taken, then the radical axis bisects that common tangent. That is, PA will be equal to PB. But the condition here is that common tangent is assumed to be not perpendicular to the line joining the centers. We assume that this line is not perpendicular to this. Common tangent is not perpendicular to the line joining the centers. If it is perpendicular, then we don't have the property which can be proved. So this is the limitation where radical axis acts as bisector with PA equal to PB. Now, not only that, this common tangent, we know that when two circles are disjoint, we have four common tangents. Say if I have the tangent this, then in this case also we have Q where this is equal to this. That is, I have this equal to this. And similarly, if I take the other tangent, then this will be equal to this. And then finally, the fourth is this. And here also we have this equal to this. So each of the common tangents will bisect, or the radical axis bisects each of the common tangent. There are four common tangents. So this equals this, and this equals this equals this, and this equals this are the four types of bisections which we identify through the radical axis out here. So radical axis bisects the common tangents. Now let's see one of the property where I can connect the circle with radical center and length of tangent. So let's see how we can connect the radical center and length of tangent in understanding or identifying the geometrical property involved connecting radical center and length of tangent with the circle. Say for example, I have three circles, 1, 2, and 3, which are not collinear. That is, this is with center C1, center C2, and center C3. Now we know that the radical center for these three circles is the point of intersection of all the radical axes taken in pairs. So I take these two circles, I have the intersection which comes somewhere in the middle, and this is the radical center, which we have discussed in the previous session. Now, if I just have from radical center, if I have the length of tangent, that is from here each of the tangents are equal, this, and this are equal, then if I take the measurement of this length of tangent from here, here, and here, the point of contacts, I can draw a circle. So if I take the radical center as the center and the radius as the length of tangent and draw a circle, I get a circle in this form. Is how we get the circle. Now this property which we identify here is that if this point which I take as C and this I take as A, B and C, I clearly identify that C is the radical center and my CA, or let me take this as P, is my radical center, and my PA, which is equal to PB, which is equal to PC, are nothing but the lengths of tangents from radical center to any circle. Now this is the length of tangent from radical center to any of the circle, which is same, equal, equal, and equal. Now if I take the radical center as center of circle, and if I take the radius So if P is the center of circle with radius PA or PB or PC, because all are same, then I get a circle which is said to be orthogonal to each of the circles. The property is that if I take a circle with radical center and radius is length of tangent and draw a circle, that circle will be orthogonal to this, this and this. That's how we identify the geometrical property connecting with radical center and length of tangent. Thus, then that circle cuts all the three circles, all the three given circles orthogonally. That's how we understand the property. The circle with radical center as center of circle and radius as length of tangent will cut each of the circles at 90 degrees. So now that we have discussed in the previous session about the radical center and length of tangent connected with a circle, if suppose I have the question where I need to find the circle which is orthogonal to the given circles, then definitely this is very much connected to the previous session. If I want to find the circle which is orthogonal to the given circles, it is very simple that I find the radical center and I find the length of tangent and I get the circle with center and radius. So let's see how we can do that using the previous session. So let's take the problem which says, find the circle or the equation of the circle which cuts each of the circles, say initially x squared plus y squared plus 3x plus 2y plus 1 equal to 0, and next x squared plus y squared minus x plus 6y plus 5 equal to 0, and thirdly x squared plus y squared plus 5x minus 8y plus 15 equal to 0. Orthogonally is the question out here. So I have to find the circle which cuts each of the circles orthogonally. So in this case, we have already discussed that if I have three circles, say circle 1 which is this, denoted by S, S dash and S double dash. So if this is the first circle, S equals 0, and this is the circle S dash equals 0, the second circle, and I have one more circle that is S double dash equal to 0, that is the third circle, then I have to find the equation of the circle which cuts each of the circles orthogonally at 90, 90 and 90. So we know that there's only one circle which cuts each of them orthogonally, whose center is radical center of these three circles, and its radius is the length of tangent from any of the circle. So if I can find the radius, or I can find any of this radius from here to here or from here to here, then I can find the length of tangent which is the radius and the center of the circle which is the radical center, and then equation of circle is obtained. So let's see how we can do that for this problem. So in order to find the radical center, my target is to first find the radical center and the length of tangent. So in order to find the radical center, I find the radical axis of this and the radical axis of one of them here, and then the point of intersection of the two radical axes gives me the radical center. So it is your choice whether you take the pair of these circles or this circles to find the radical center. So I'll be taking first this or this in finding the radical center. So initially my radical axis for s equal to 0 and s dash equal to 0 is what I'm going to find initially. So how do I find the radical axis of these two circles? We clearly know that the radical axis is given by s minus s dash equal to 0, where s is this and s dash is this. So s minus s dash implies this minus this gives 3x minus this 4x plus 2y minus 6y is minus 4y plus 1 minus 5. Therefore, this on further simplification gives x minus y equals 1, which I take as equation 1. So one of the radical axes of s and s dash is given by equation 1 as obtained there. Similarly, I would like to find the radical axis of s and s double dash, which would be equation 2. So finding the radical axis and s double dash, s and s double dash is nothing but s minus s double dash equal to 0. So this on subtraction gives me the radical axis of this and this, which is nothing but here, as can be seen in the diagram. So as we know that s is here and s double dash is here, when I subtract 3x minus 5x gives me minus 2x, and 2y minus of minus 8y, which is plus 8y, gives me 10y, that is 1 minus 15, which gives me minus 14 equals 0. Now this is equation 2 when I simplify this more further. That implies I can write this by dividing the whole equation by minus 2. I get this as x minus 5y equals minus 7, and this is equation 2, which is nothing but the radical axis of s and s double dash. Now the question comes on finding the radical axis, which is nothing but the intersection of this radical axis and this radical axis. So solving 1 and 2, I get the point of intersection C through the elimination method. Now let's find the radical center by solving equation 1 and equation 2. So solving this using the elimination method, I subtract so that this gets cancelled and I get 4y equals 7 plus 1, 8. That implies y equals 2. And when y equals 2, substituting in 1, I get this to be x minus y equals 1. That implies x equal to 3. Therefore, y is 2 and x is 3. And therefore, radical center denoted by C out here is given by the coordinates 3, 2 is what we get. The radical center is given by 3, 2. So now that we have got the radical center, which is 3, 2, will act as the center of the required circle. Now next comes in finding the radius. In order to find the equation of the circle, we need the center, which is already known, but the radius, which is unknown. So therefore, as we have seen in the previous session on the geometrical properties, radius is nothing but the length of tangent from center to any of the 3 circles, because it is the equal distance from each of the circles. My radius which is length of tangent from C32 to say I take S equal to 0. I take the first circle, that is S equal to 0, which is nothing but, if I take this as A, B, C, then this is nothing but CA, which is given by the formula root S11. Now this is strictly from the formula which we have on finding the length of tangent, which is given by root S11. So how do we find this? Using the formula. Root S11 is nothing but substituting this point in the circle. That is, in place of x, I put 3. In place of y, I put 2. So this reduces to x squared, which is 3 squared, plus y squared, which is 2 squared, which on simplification gives 9 plus 4 plus it is 9 plus 4 plus 1, which is nothing but is 3 root 3. So the radius of the required circle is 3 times root 3, and the center of the required circle is 3, 2, and the radius is 3 root 3. So using the radius and center, we can now easily find the equation of the required circle. So therefore, for the required circle, the center is 3, 2, and radius is 3 root 3. Therefore, equation of circle which is orthogonal to all the 3 given circles, that is, equation of required circle, is given by x minus 3 whole square plus y minus 2 whole square equals r square. Now this is the formula. When center and radius is given, we have x minus a whole square plus y minus b whole square equal to r square, which on simplification gives x squared plus 9 minus 6x plus y squared plus 4 minus 4y equals 27. And this on further simplification gives x squared plus y squared minus 6x minus 4y plus 13 minus 27, which is the required circle in the general form of representation. So this is how we find the equation of a circle which is orthogonal to all the other 3 circles, by finding the radical center and the radius, which is the length of tangent. So geometrical property helps in finding a circle orthogonal to all 3 circles using the length of tangent and the radical center of radical axis.